Hello my lovely students, you are welcome to a new lesson. Today, I shall be teaching you linear inequalities 2, and we shall be learning about graphs of linear inequalities in two variables. From definition, inequality is a mathematical statement that two algebraic expressions are not equal. Please note that linear inequalities in two variables can be represented on a Cartesian plane graph with x and y axes. From the table displayed here, we have the four inequality symbols, their boundary lines, and how they are displayed on a Cartesian plane graph. The first inequality symbol means is greater than, and the boundary line is a broken line. The second inequality symbol means is less than, and the boundary line is also a broken line. The third inequality symbol means is greater than or equal to, and the boundary line is a solid line. While the fourth inequality symbol means is less than or equal to, and the boundary line is also a solid line. Please take note of this information as we learn more about graphs of linear inequalities in two variables. Please note the following points about graphs of linear inequalities in two variables. Point number 1. In the graph of linear inequalities on a Cartesian plane graph, the unrequired or unwanted region is usually shaded. This is done so that the required or wanted region is left unshaded and clearly visible. Point number 2. Every point in the unshaded region is required, wanted, and satisfies the linear inequality. The graph of linear inequalities in two variables displayed here is an example of what we are about to learn today. Moving on, let's see our first example on graphs of linear inequalities in two variables. Example 1. Sketch the following inequalities on a Cartesian plane. Question A. X is less than 4. Question B. X is greater than minus 1. Question C. X is less than or equal to minus 2. Question D. Y is greater than minus 3. And question E. Y is less than or equal to 5. Let's see the solution to question 1a. The graph of x is less than 4. What kind of boundary line do you think will be involved here? Is it a broken line or a solid line? Let's see if you are right. The graph of x is less than 4 involves a broken line going through the point 4 on the x-axis. That should be a vertical broken line. Of course, the inequality is x is less than 4, so the numbers required are the numbers less than 4 on the x-axis. Such numbers are 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4, and so on to the left-hand side of the number line for x. So the numbers that are not required here are numbers greater than 4, such as 5, 6, 7, 8, 9, 10, and so on to the right of the number line for x. Since we are shading off the region that is not required, we will shade off the region to the right of the broken line and leave the region to the left of the broken line unshaded for x is less than 4. Next, let's see the graph of x is greater than minus 1. Once again, which type of boundary line will be required here? Is it a broken line or a solid line? Let's see if you are right again. Of course, for the graph of x is greater than minus 1, the boundary line required is a broken line. This broken line should go through the point minus 1 on the x-axis. Now for x is greater than minus 1, the numbers required are numbers like 0, 1, 2, 3, 4, and so on to the right of the number line for x. While the unrequired numbers for x is greater than -1 are the numbers to the left of the number line for -1. Such numbers are -2, -3, -4, -5, and so on to the left. Since we are shading off the region that is unrequired, we will shade off the left hand side of the broken line and leave the right hand side of the broken line, which represents the required numbers, unshaded for x is greater than -1. Next, let's see the solution to question 1c. The graph of x is less than or equal to -2. In this graph, which kind of boundary line is needed? Is it a broken line or a solid line? Let's see if you are right. Of course, for x is less than or equal to -2, a solid line is required as the boundary line here. I hope you got that right. The solid line should go through the point -2 on the x-axis. That should be a vertical line. Looking at the inequality again, x is less than or equal to -2. The numbers required here are numbers less than -2, which are -3, -4, -5, and to the left of the x-axis line. While the numbers that are not required are the numbers that are greater than -2. Such numbers are -1, 0, 1, 2, 3, and so on to the right of the number line. Don't forget, we are shading off the unrequired region, so we will shade off the right hand side of the solid boundary line and leave out the left hand side unshaded as the required or wanted region for x is less than or equal to -2. Let's see the solution to question 1d. The graph of y is greater than -3. Once again, what type of boundary line will be required here? Is it a broken line or a solid line? Let's see if you are right. For the graph of y is greater than -3, a broken line will be required through the point -3 on the y-axis. That should be a horizontal line going through the y-axis at the point -3. From the inequality, y is greater than -3, the numbers that are required are the numbers bigger than -3 on the y-axis. Such numbers are -2, -1, 0, 1, 2, 3, 4, and so on above the line through the point -3. While the numbers that are not required here are the numbers that are less than -3 on the y-axis. Such numbers are -4, -5, -6, -7, and below the line through the point -3. Since we are shading off the unrequired region, we are going to shade the region below the broken line through -3 and leave out the region above the broken line as the required region, while the region above the broken line remains unshaded as the required region for y is greater than -3. Let's see the solution to question 1e. The graph of y is less than or equal to 5. Once again, what kind of boundary line would be required here? Would it be a broken line or a solid line? Let's see. For y is less than or equal to 5, a solid boundary line will be required through the point 5 on the y-axis. That line should be a horizontal line going through the y-axis at point 5. The required numbers are numbers less than 5, which are 4, 3, 2, 1, 0, -1, -2, and so on down the number line for y. While the unrequired region should be the numbers that are greater than 5 on the y-axis. such as 6, 7, 8, 9, 10 and so on above the y-axis. Since we are shading off the unrequired region, we will shade off the region above the solid boundary line, while the region below the solid line will be left unshaded as the required region for y is less than or equal to 5. I hope all the solutions to example 1 they are clear to you. Moving on, let's see our second example. Example 2. Show on a graph the region that contains the set of points for which 2x plus y is less than 3. Let's see the solution to example 2. From the solution, the inequality is 2x plus y is less than 3. Now we are going to replace the inequality symbol less than with the equality symbol, so that we will have 2x plus y is equal to 3. Hence, the linear inequality has been changed to a linear equation. Next, we are going to draw the graph of the linear equation 2x plus y is equal to 3. In doing that, let's know where the line will cross the y-axis. To get this point, we are going to substitute x is equal to 0 into the equation 2x plus y is equal to 3. That will give us 2 times 0 plus y is equal to 3. That gives y equal to 3. In other words, when x is equal to 0, y is equal to 3. So we are going to plot the points x is 0, y is 3 on the y-axis. Next, let's know where the graph of the linear equation 2x plus y is equal to 3 will cross the x-axis. To get this point, we are going to substitute y is equal to 0 into the linear equation. When we do this, we are going to have 2x plus 0 is equal to 3. That will give us 2x is equal to 3. Dividing both sides by 2, we are going to have x is equal to 3 over 2, which is 1.5. In other words, when x is equal to 1.5, y is equal to 0. So we are going to plot the points x is 1.5 and y is 0 on the x-axis. When we plot these points along both x and y axis, what kind of linear graph are we going to get? Let's see. When we plot the points 3 along the y-axis and 1.5 along the x-axis, we are going to have this kind of linear graph. Of course, the initial linear inequality is 2x plus y is less than 3. So for less than, the boundary line involved should be a broken line. So we are going to join the points 3 on the y-axis and 1.5 on the x-axis with a broken line. Next, how do we tell the region we are going to shade off? Should it be the right hand side of the broken line or the left hand side of the broken line? Let's see. To know the side of the broken line that we are going to shade off or leave unshaded, we are going to test both sides of the broken line. To start with, let's test the left hand side of the broken line with any convenient point on the left hand side. Here we are testing with the point x is 0, y is 0, representing the origin on the left hand side of the broken line. We are going to test by substituting these values into the original linear inequality, which is 2x plus y is less than 3. When we substitute x is 0 and y is 0 here, we are going to have 2 times 0 plus 0 is less than 3. That should give us 0 is less than 3. Of course, 0 is less than 3 is true. That makes the left hand side of the broken line to be the required or unshaded region. Also, let's test the right hand side of the broken line with any convenient point. Here we are using the point x is 2, y is 0. When you substitute these values x is 2, y is 0 into the linear inequality 2x plus y is less than 3, what are you going to find? Will the statement be true or false? Let's see if you are right. Of course, when we substitute the values x is 2 and y is 0 into the inequality 2x plus y is less than 3, the statement will be false, because we are going to have the statement 4 is less than 3. But 4 is actually not less than 3, so that statement is false. That makes the right hand side of the broken line to be the unrequired or shaded region. I hope you got that right. For the final solution to example 2, the points below the broken line 2x plus y is less than 3 represents the solution set. The region above the broken line is shaded to show that it is not required. I hope the solution to example 2 is clear to you. Moving on, let's see our third example. Example 3. In the following diagrams, find the inequalities that describe the unshaded region. In question A, we have a solid line through the point 1 on the x-axis with the left-hand side shaded. In question B, we have a broken line through the point -1 on the y-axis with the bottom of the line shaded. While in question C, we have a broken line through the point -2 on the x-axis with the right hand side shaded. Let's see the solution to question 3. For question 3a, since the boundary line is a solid line, do you think the inequality will involve equal to or not? Let's see if you are right. For question A, the inequality is x is greater than or equal to 1. This is because the numbers greater than 1 are the unshaded numbers. And since the boundary line is a solid line, it will involve greater than or equal to. I hope you got that right. Next, for question B, since the boundary line involves a broken line, do you think the inequality will involve equal to or not? Let's see if you are right. For question B, the inequality is y is greater than -1. This is so because the numbers greater than -1 on the y-axis are the unshaded and required numbers. And since the boundary line is a broken line, and equal to is not required in the inequality. So the inequality for question B remains y is greater than -1. I hope you got that right again. Next, for question 3c, the graph involves a broken boundary line. Once again, do you think the inequality will involve equal to or not? Let's see if you are right. For question 3c, the inequality is x is less than -2. Once again, this is so because the region less than -2 on the x-axis is the unshaded or required region. And since the boundary line is a broken line, an equal to is not needed in the inequality. That makes the inequality x is less than -2. I hope all the solutions to example 3, they are all clear to you. Let's see our fourth example for graphs of linear inequalities in two variables. Example 4. Find the inequality that describes the unshaded region in the linear graph displayed here. We have a solid line going through the point 2 on the y-axis and -2 on the x-axis, and the right hand side of the solid line is shaded while the left hand side of the solid line is unshaded. Let's see the solution to example 4. Here in the graph, since we have a straight line, let's find the equation of the straight line. The equation of a straight line is y is equal to mx plus c, In this equation, m represents the gradient of the straight line. The formula for the gradient of a straight line is y2 minus y1 over x2 minus x1, or it could be y1 minus y2 over x1 minus x2. Also, c in the straight line equation represents the intercept on the y-axis by the line. From the graph, we need 2 points to get our x1, y1 and x2, y2. Let our first point be the point x is minus 2 and y is 0. Represent the point where the line crosses the x-axis. Also, let our point 2 be the point x is 0 and y is 2, representing the point where the straight line crosses the y-axis. When we substitute these values into our gradient formula, what will be the gradient of the straight line? Let's see if you are right. Substituting the values x1 is equal to minus 2, y1 is 0, and x2 is equal to 0, y2 is 2 into the formula for the gradient y2 minus y1 divided by x2 minus x1, we are going to have the gradient m as 1. Also, from the graph, since the straight line crosses the y-intercept at the point 2, the value for c representing the intercept on the y-axis is 2. Next, when we substitute the values m is equal to 1 and c is equal to 2 into our formula for the equation of a straight line, what will be the equation of the straight line in the linear graph in example 4? Let's see if you are right. Of course, the equation of the straight line is y is equal to mx plus c. Substituting 1 for m and 2 for c in the equation of the straight line, we are going to have the equation y is equal to x plus 2. I hope you got that right. Next, we are going to test the unshaded region, which is the left hand side of the solid line, with a convenient point to tell whether the inequality will involve greater than or equal to or less than or equal to, since we have a solid boundary line in the linear graph. Here we are testing with x is minus 4 and y is 0 as our convenient point in the unshaded region. Here we are substituting x is equal to minus 4 and y is equal to 0 into the inequality y on the left and x plus 2 on the right. That will give us 0 on the left and minus 4 plus 2 on the right, which will give us 0 on the left and minus 2 on the right. When you compare 0 on the left and minus 2 on the right, you will see that it is only when it is 0 is greater than or equal to minus 2 that it will be true. Hence, for the required or the unshaded region, the inequality should be greater than or equal to. Next, we are going to replace the initial equation with the inequality greater than or equal to, representing the solid boundary line. Lastly, the required inequality for the linear graph displayed in example 4 is y is greater than or equal to x plus 2. I hope the solution to example 4 is clear to you. Finally, let's see the application of linear inequalities in real life, talking about linear programming. Point number 1. Linear programming is a graphical method for solving problems involving several limits or conditions that need to be satisfied at the same time. Point number 2. Linear programming uses graphs of linear inequalities to solve problems that involve constraints or restrictions. Point number 3. Linear programming usually involves either maximizing or minimizing the objective function. Point number 4. Linear programming methods are employed in business management and in many industries to determine how to maximize profits or minimize production costs. Please take note of all these points involving linear programming as an application of linear inequalities in real life. Thank you very much for going through the lesson today. I want to advise that for you to get more information about the topic Linear Inequalities 2 involving graphs of linear inequalities in two variables, please continue to read your textbook. Don't forget to attempt your quiz and your assignment. I hope to see you again in our next class. Until then, it is goodbye for now. Thank you very much.